Alright guys, so what we're going to go ahead and do is we're going to go through our notes here, and we're going to title the section is going to be 1.2, okay, and we're going to entitle it Limits. Let me make sure this is actually working here, see if this is actually recording. Yeah, it looks like it's recording. Okay, so limits, and today we're just going to talk about more of an intuitive approach. Yeah, is it kind of hard to see? Is it better if you turn off? It's not that for me. Is that better? Yeah. Thank you very much, guys. So today we're just going to talk about if we visually look at something like on a graph or a table, what does it seem to be approaching our limit? Okay, again, like I said, it doesn't matter what actually happens at that point. It's what are you approaching as you get very, very, very close to that point. Just like with derivatives, remember as the change in x got smaller and smaller and smaller and smaller, we were finding that value or a limit that we were approaching. Okay? Or with definite integrals, as the number of trapezoids got very, very, very large, we were approaching some number called our limit as well. Okay? So we're going to kind of go back from there. So I'll just underline this. All right, so first thing is let's go ahead and define what a limit is. So Roman numeral 1, I'm going to say a limit is the value the function approaches as its x values approach a point. And today we're going to talk specifically about how we use a graph and also a table to help find out what a limit is going to be. All right, so let's look at an example to kind of talk about what's going on here. So example 1. I'm going to ask you to find, this is the notation that we use. It says the limit as x approaches 2. Bless you. Okay. So that just basically means that as you get closer and closer to 2 for our function, what does it look like our function is approaching? So here's the function I'm going to give you. It is going to be x squared minus 2x minus 8 all over x minus 2, and that's going to be multiplied by 2. Okay. Now, before we even start looking at the limit, looking at the graph, looking at the table of values, do you think it's going to work just to plug 2 into this equation? No, right? We're going to have some issues. It's going to end up being undefined. So we can't just substitute it in. So we're going to actually create a table of values. And what we're going to do here. Yeah, what's up?
You got something like this, and could you simplify the?
So let's see, if we were to factor up here, what would we get?
Yeah, x minus 4. X minus 4.
Yeah, I don't know if that's going to work out for this one. Yeah, if it was x plus 2 down here, then that would be fine. All right, so we're going to have x and we're going to have y. Or I guess this is more called, for using function notation, f of x. Okay. So we're going to get values that are right before 2 and values that are right after 2. Okay. So what's going to happen is, let's go ahead and do, a value right before 2 could be like 1.9, right? If I was wanting to get a little bit closer, could I do 1.99? Yep, could do that, so 1.99. And if I did 1.999, that's going to be even closer, right? And at 2, I also put that in my table, but I know that I'm just going to cross it out because it's not going to really give, it's not going to work for my function. And then how about something right after 2? Yeah, 2.001, right? And then how about if we did 2.01 and 2.1? So why don't you enter this into your graphing calculator? And you guys know how to use your table of values where you can change it to ask. Oh, you know what? Connor, you are correct. I did want a plus here. Because what's going to end up happening is I do have, what do I have at that point if I make it plus? Yeah, we do have, if you were to factor up here, it would be x plus 4 and x minus 2. I'm just changing it to plus. I realized for my example I want to have a plus there, Oliver. Sorry. Yeah, so what ends up happening is the x minus 2's get crossed out, On your graph, when that happens, you have something called a hole there. Remember in the video when it was approaching that, it had that hole, right? Because it could be factored and crossed out. So go ahead and enter this in. If you want to look at your graph, you can see what it looks like as well. You know what? Leave it as the original one. I'm just going to cross this out because that was just kind of a side note. Leave it as the original one. It shouldn't matter if you put it in factored form. Either way, it should work out for you. All right, so I'm going to put it into y equals here. And I'm going to have x squared plus 2x minus 8 divided by 2 parentheses. Guys, make sure you're using your parentheses correctly. Okay. I don't know. Your calculator might be different than mine. And then for your table set, you can change it to ask. And if you go to your table, I'm going to put in 1.9, 1.99, 1.999, 2.001, 2.01. This is, yeah, sorry. Matt, make sure it's x squared plus 2x minus 8. I made a mistake there. Should have been a plus. Okay. So go ahead and fill in your table and see what value it seems to be approaching. What's up? What does it look like it's approaching? 3, right?
I did it.
And if you were to look at your graph, so zoom 6, it's not going to show you your whole Connor, but you should still see that it's approaching 3 as x approaches 2.
Yeah, my hole is not shown.
Just mine, I have a hole.
So guys, at 1.9, we have 2.95. 1.99, we have 2.995. Your answer would end up just being 3. It's approaching 3.
On the table.
On the table,
It doesn't matter if it's x or 3.
does it matter if it's x or 3?
When you wrote it out, it's silly.
Yep.
It doesn't matter if it's x, like underneath it. No, x is
Here?
like on top of the table.
Yeah.
Like where x is 2 and then f of x is x. Doesn't matter if it's
Oh, you need to keep it. I want you to show that you're approaching 3. Okay, so keep it exact, Connor. So yeah, guys, your table is kind of your proof that it's approaching 3. So I don't want you just writing down 3, 3, 3, 3, 3. I want you to show me that it's, 2.95, 2.995, 2.9995. We're getting really close to it. Okay? All right. Well, again, remember, when you're looking at the limit, it's not the actual spot. It's as you approach it. All right, let's look at another example. So example 2. All right, I'm going to give you f of x equals, it's going to be my original function, so x squared plus 2x minus 8 all over 2 times x minus 2. And I'm going to tell you for this piecewise function, this is true as long as x does not equal 2. Okay? When x does equal 2, I'm going to tell you that it equals 3. Okay? Sure. Yep, so basically what this says for the piecewise function, sorry about that, Will. Let me move it down a little bit. Okay? As long as x does not equal 2, you're using this one right here, right? But when x equals 2, it's going to equal 3. What am I doing really, guys? If I have that hole, what am I doing to it, Matt? I'm just filling it in, exactly. What's that? Okay. All right, so if I were to ask you, what does f of 2 actually equal in this case, guys? 3, good. How about if I asked you what is the limit as x approaches 2 of f of x? What is it going to equal? 3 as well. Alright, so you can kind of see there, those are some examples of as we approach it. What we're going to talk about is what happens when a limit does not exist. Okay, so what happens when you don't approach the same value from both, like, the left and right hand side. So I'm going to show you a short video clip for that as well.
Do you have an author of these videos?
I don't know. You could probably go to his website and see.